Hey everyone, Miss Butler here. I have a video on weak acid and weak base equilibrium. So here are some of our goals. We want to be able to write equilibrium expressions for weak acid and bases, figure out the pH or pOH of weak acids and bases using Ka and Kb expressions, define percent ionization and figure out what it is and how it relates to strength, calculate concentration from percent ionization or percent ionization when we know the pH, and then find pH of polyprotic acids. We might touch on this a little bit later, not huge in this video, but that's all right. So in our equilibrium unit, we saw K expressions, right? K at equilibrium, where the forward rate equals the reverse rate, and we can write a K expression for products divided by reactants. Well, we can do the same thing for acid and base equilibrium. If it's an acid, we call it Ka. If it's a base, we call it Kb when it's at equilibrium. So same ideas here, but just specifically for acids and specifically for bases. Okay. In water, weak acids do not dissociate or ionize 100%, but they do a little bit. So here's what I mean. When we have a strong acid, the definition of a strong acid, those acids that are on our list of strong acids that we're memorizing, when we put them in water, they break apart 100%. So if I have 2.0 molar of this, I have 2.0 molar of this, and 2.0 molar of this if it is strong. If it is weak, we only get a little tiny bit that actually breaks off, but for the most part, we are in the acid form. So right now, we're going to say that this is a weak acid, and it doesn't break off 100%. So this is a dissociation reaction with the weak acid in water to break apart a little bit into H plus and whatever the other piece is, so we're just calling it X minus. So we know that our K expression at equilibrium, K is always equal to products divided by reactants. So Ka is no different. It is just specific for this type of reaction with a weak acid breaking apart into H plus and whatever the other piece is. So Ka, the dissociation of a weak acid at equilibrium, is the products H plus and X minus, those concentrations, divided by the reactant, the acid, HX. Don't forget that we can always write a weak acid dissociating in water like this, with water, which is liquid, and then we would get H3O plus, which is the same as H plus, and X minus. And in that case, this and this are the same, and when we write our K expression, products H3O plus, X minus, over, remember, no lurking liquids in our K expression, so just HX. And so you can see when we assume that H plus is the same as H3O plus, that these expressions are essentially the same. All right, we can do the same thing for weak bases. So in this case, this ion X minus is a weak base. And so when I put it in water, we're going to make HX and OH minus. So that's what makes X minus a base, is when it's put in water, it produces OH minus, even though there's no OH minus in this directly. Anyways, weak bases will not break apart 100%. So we won't get, if this is 2 molar, we won't get fully 2 molar of OH minus because it's weak. But we can still do products divided by reactants. Notice X minus is our base. H2O would be our acid in this reaction. And there's no H2O in Kb expression because it is liquid. Okay, notice this section is called using Ka to find pH. So that means for weak acids and weak bases, we cannot use the pH square, and that's what I call like the negative log of H plus is pH, 10 to the negative pH is H plus, right? That pH square we learned earlier. So we can't use that pH square to find the pH of weak acids or the pOH of weak bases. Here's why. if we have a strong acid, let's say, for example, I have 2 molar of HCl. What that means is because strong acids break apart 100%, right? I get 2.0 molar of H plus, and I have 2.0 molar of Cl minus ions. It is 100% dissociation. Or ionization is another word we'll see later. But what about a weak acid? Let's say I have 2.0 molar HF. Well, because it doesn't break apart 100%, it means I won't have 2.0 molar H plus or 2.0 molar F minus. Not all HF breaks into ions. In fact, weak acids typically are less than 5%. So less than 5% of this 2 molar is actually going to break into the ions. So we have to have a different way to find pH. I can't just take the negative log of 2 like I can for strong, right? Negative log of 2 would give me the pH. I can't do that here. So this is the connection now between acid-base and equilibrium. So their first step to find the pH of a weak acid is to write the dissociation reaction. So that's the acid breaking apart into the ions, and then the Ka expression. Then you are going to use an ice table. So we should set up our ice table. And so really you kind of get your ice table set up with your starting concentration, 0 for the products, your minus X's, your plus X's. Then you're going to plug in any values that you get into your Ka expression and solve for X. So do a little algebra. And then X is going to be your concentration of H plus at equilibrium. So weak acid and weak base use concentration of H plus at equilibrium, or concentration of OH minus if it's a weak base at equilibrium, and then your pH square. In the pH square, not initial conditions. So the main difference is if I have a 2 molar weak acid, I'm not going to take the negative log of 2. I'm going to do an ice table and solve for the equilibrium concentration and then take the negative log of that. So we'll do lots of examples. So here's a typical problem. Find the pH of a 0.2 molar solution of HCN, and they give me the Ka value. HCN is a weak acid. How do I know? There's 2 clues. 1, they gave me a Ka value. 2, it is not on my list of strong acids. So that list that we gave you earlier this unit of strong acids, if it's not on that list, you're going to assume it's weak. So any weird acid names, you assume it's weak because it's not on that list. So anyways, if I had 0.2 molar of HCl, that would mean I would have 0.2 molar of H plus, because HCl is a strong acid. So when I put a strong acid in water, it breaks apart 100%. With HCN, it is a weak acid, so when we put it in water, only a little bit of H plus and a little bit of Cn minus will pop off, but most of it will stay together. So here's what we now can set up. We'll do our ice table, set that bad boy up. So they told me, initially, I have 0.2 molar of this. Initially, before it's in the water, I don't have any of this in this. And now we just use our stoich. And this is nice and easy because it's all 1 to 1. So I'm going to use up 1 times X because we move towards the 0, so we move this way. Use up this guy, add 1X, add 1X. And then my equilibrium line, remember I plus C equals E. So we get 0.2 minus 1x, 1x, because 0 plus 1x, and 0 plus 1x is just 1x. So my Ka expression, products, H plus, Cn minus, divided by HCN. And remember, K means equilibrium, so these are really the equilibrium numbers. I can put little EQ. We're only going to use the E line for our Ka expression. Luckily, they told me that the Ka is 4.9 times 10 to the negative 10th. And just a reminder, that means that reactants are favored at equilibrium. Because K is less than 1, right? So that really means this is favored. Really, it's staying together at equilibrium. Not a whole lot is dropping off. Anyways, let's plug in our equilibrium values. So we get X times X over 0.2 minus 1X. Luckily, I can omit this guy because of the 5% rule. We'll check that later because Ka is small. So let's kind of reset up our equation then. We should get 4.9 times 10 to the negative 10th equals x squared over 0.2. I'm going to do a little algebra. So crisscross multiply, take the square root, and I get x is equal to 9.9 times 10 to the negative 6. What I mostly care about is plugging in x. So if we plug that x value in to our equilibrium, we can find the concentrations of everything. So the equilibrium concentration of HCN is equal to 0.2 minus 1 times 9.9 times 10 to the negative 6. So that gives me some really small, like essentially 0.2, because I'm basically taking 0.2 minus something so small, sig fig wise. And then we can do the same for H plus at equilibrium and Cn minus at equilibrium. I'm saying those are equal because they're both 1x. So that equals 9.9 times 10 to the negative 6 molar. So we're going to use that number here because it's the concentration of H plus to find our pH. So we can take the negative log. So pH is the negative log of H plus at equilibrium. So pH is equal to the negative log of 9.9 times 10 to the negative 6. pH is equal to 5.00, and that is my final answer for this. Real quick, let's check the 5% rule. So we omitted 1 times x, so we omitted 1 times 9.9 times 10 to the negative 6. What did we omit it from? 0.2. So basically, I need to make sure that when I omitted this x from 0.2, I want to make sure it's less than 5%. So I want to make sure I'm omitting less than 5% of what I started with. And in this case, it is 0.000495%, which is way less than 5%. So we are valid in our omission. We don't have to go and do a quadratic formula. So there's a typical problem. So here's that same problem worked out again if you want to look through it one more time. Okay, I want you to try this one. A 0.1 molar formic acid solution. I've never heard of formic acid, so it must be weak. And they give us a pH of 2.38. What is the Ka? So here's what I would like you to do. I want you to set up your ice table. So write the reaction, the dissociation reaction, set up your ice table and your Ka expression. So pause the video and do that, and then we'll jump in together to figure out how to use that pH number. So notice in this problem, they want us to find the Ka. They did not give it to us. So a lot of times when you're trying to find Ka, they have to give you clues as to what X is. So in an acid-base problem, some typical information that they will give you to help you find X so that you can plug in and solve for Ka is the pH. Because if I know the pH, I can know H plus at equilibrium, which is the same as X. So let's start with our ice table. I think I can move this. All right, so here's my formic acid formula, which was given. The reaction for Ka is always that front H popping off and then whatever is left over. We started with 0.1 that was given to us and nothing. So we're going to move towards the zeros, use this up, make this. And so then I can write my Ka expression, products divided by reactants, and I can plug in. The only issue is I don't know Ka and I don't know X. But they gave us a helpful clue. They said that the pH is 2.38. That means the pH at equilibrium is 2.38. Well, the H plus at equilibrium, using our pH square, H plus is 10 to the negative pH. So I can take 10 to the negative 2.38, and I get H plus at equilibrium And we know H plus at equilibrium is the same thing as X. Look at your ice table. H plus at equilibrium is equal to X. So then we know X. Let's just plug X in to our K expression. So I plugged in X for each guy on the top, X and X right here and here, 0.1 minus X, 0.1 minus X, and then we can solve for our Ka value. A note about the magnitude, so the size of Ka. A big Ka means it's a stronger or less weak acid, meaning it breaks apart more. A small Ka means it's a weaker acid, meaning the acid stays together, the H doesn't pop off as easily. Okay, this is just like the one that we did, so I'm not going to talk through all the details. I want you to pause the video, see if you can do this one on your own. Here's the acidic H plus that you pop off. So you'll have this as H plus and this with a minus charge. But I want you to try this one, pause the video, and I'll put up the answer in 3, 2, 1. So there is your ice table with your dissociation reaction, your Ka expression. I was able to find X using the 10 to the negative pH, because that's your equilibrium of H plus. So once I know X, I can plug into the Ka expression and solve. So hopefully this is what you got. Try to zoom that out. So here are two acids with Ka values, which is stronger and why. You are able to compare Kas directly. So a big Ka means it's a stronger or less weak acid. A small Ka means a weaker acid. So in this case, HC2H3O2 is a stronger acid because it has a larger Ka. It's only to the negative 5th versus negative 10th. So that means for this guy, the H plus, this H plus here, pops off a little bit easier than the H on HCN. All right, the last kind of topic is percent ionization. Sometimes it's also called percent dissociation. And this is all about how much of the H plus is breaking off of the acid. So a strong acid has 100% ionization. A weak acid maybe has less than 5%. And so the stronger the acid, the higher percent of H plus popping off. The weaker the acid, the lower the percentage. So this is usually a follow-up question to the problems we've just done. So you're going to kind of follow the same steps. Write the dissociation reaction, right? H plus popping off. Use ice and Ka to find what X is. So you solve for X. Once you know what X is, you are going to take that value and divide it by the initial concentration of the acid and times it by 100. That will tell us what percent of the acid popped off. Notice this equation is the same as the 5% rule. And the goal, or what it's useful for, is it tells us what percent of acid dissociated or ionized. Whoops. So, calculate the percent ionization of propanoic acid with 0.25 molarity, and they give us the Ka. So here's what I would like you to do. I want you to write the reaction. I want you to set up your ice table. I want you to set up your Ka expression. I want you to solve for X, which we know is the same as H plus at equilibrium. Once you get that far, I will help you with that last step of finding percent ionization, but you should be able to do these 4 things based off the earlier part of this video. So pause, and when you think you got all 4 steps done, jump back on. All right, here we go. So we have our reaction set up, breaking it down, H plus and the anion, the negative charge. We have our ice table with everything plugged in. We have our Ka expression. We know what Ka is, so all we have to do is solve for X. Notice Ka is to the negative 5th or smaller, so we can omit. So we'll go back and check that later. Then we do a little algebra and solve for X. X is the same as our concentration of H plus at equilibrium, but they just want the percent ionization. So hopefully you got this far. Percent ionization, remember, is X, whatever X is, try that again, whatever X is divided by the starting concentration. So if you look, I want to know essentially what percent of this acid broke down. What is the percent of minus X from what we started with? So I'm going to take X divided by 0.25. So 1.8 times 10 to the negative third divided by 0.25 times that by 100, I get a very small 0.721% ionization. Notice this is the same as the 5% rule because we omitted x from 0.25. So we would take x divided by 0.25. So you don't need to do the 5% rule on a question like this. You can use the answer for both pieces. So here's my answer, and I'm also saying it's less than 5%, so my omit here was valid. All right, a 0.15 molar weak acid solution is 3% dissociated. Calculate the Ka and pH values. So let's look at this problem. Remember, if they don't give us Ka, they have to give us other ways to find X. So when they tell you the percent dissociation, that's a helpful way to find X. So let's actually figure out what X is. 3%, right, that's our percent dissociation, has to equal whatever X is divided by the starting concentration, because this is our equation for percent ionization or for percent dissociation. So if we do a little algebra and solve for X, we get X is 0.0045 molar. What that tells me, that is H plus at equilibrium. So I set up my ice table, right? We had 0.15, we had 0, we had 0. We know what X is, so I can plug in X, right? So our Ka expression, I plugged in our equilibrium, but we know what X is. So now all I have to do is plug in, kind of scroll down, plug in for x and 0.15 minus x, that's what I did right here in red, to solve for my Ka. To find the pH, we know x is the same as H plus at equilibrium, so we're going to take the negative log of that to find my pH. All right, this is a multi-part problem. We have the Ka, the acid dissociation constant, is the same as Ka, so this is Ka. I want to know equilibrium concentrations, and that's it. And they gave me the initial, the starting molarity. So first step, always write the reaction. I wrote the acid breaking apart. I set up my ice table with the starting values. I wrote my Ka expression, and we know what Ka is, so I solve for X. Once we have X, we can find the equilibrium concentrations by plugging X in. So I just said H plus and the anion are the same. They're equal to X at equilibrium, whereas the acid is 0.050 minus X, so we get 0.048 roughly. Part 2 is to use those equilibrium concentrations to find pH and percent ionization. Well, remember, pH of a weak acid is the negative log of the H plus at equilibrium, and we found the concentration of H plus at equilibrium on our last slide, so I take the negative log of that. Percent ionization is whatever X is divided by the starting concentration. And remember, X is H plus at equilibrium. So I'm basically taking H plus at equilibrium divided by what we started with times 100, and we get 3.5. So that means 3.5% of the acid ionized. That is very weak, right? A strong acid is 100%. Weak acid is typically less than 5, so not a whole lot of that H breaking off. All right, this is the very last problem. So I want you to figure out if we have a 0.1 molar solution of bromoacetic acid. There's that acidic H plus on the end of this guy right there. And it's 13.2% ionized. Find the equilibrium concentrations and the pH. So pause the video. If you can do this one, you are a rock star. Pause it, and I'll put the answer up in 3, 2, 1. Hopefully this is the equation you got and the ice table, and you were able to use the percent to solve for X and then plug in your X's to find the pH and the equilibrium concentrations. Please reach out if you have any questions.